Okay. Now it's
There you go.
right? Yeah, it's now recording. Yeah. So we'll begin on section 3.2, flow control. Okay. So far, what we have learned. Why is that this? Sorry, it's just the Zoom is constantly blocking the view.
Yeah.
Hide those. If you click on more,
Oh,
it says hide panel,
oh,
hide floating meeting controls too.
thanks. Yeah, thank you so much. Yeah, I think I'm even more terrible than day one at Zoom. So yeah, the codes we have seen so far are like straight in workflow. So we define two variables. For example, we define two variables, and then we run a Wilcox test. So everything is linear, like step by step. Now before I introducing to you what's flow control means, let's just take a look at this exercise that we will use throughout our section 3.2 to illustrate the idea of flow control. So after an on-site maintenance, the technician from the company you bought the machine for measuring enzyme activity just told you, oh, it's too old, and when things get too old, they begin to lose their linear tree, which means you can no longer trust the raw reads. So for those reads are actually very low, say for example below 20, then you need to multiply the read by 1.25 so as to recover the true read, because the sensor tends to underestimate the true activity when the activity is too low. And similarly, if the activity is too high, you tend to saturate the sensor, and you need to multiply the read by 0.8 to correct your reads to get the true activity. And in many cases, it would be super expensive to buy a new machine. So typically, your boss will ask you to see whether there is any way of solving this problem without causing any dollars, which is through data analysis. So let's first have some first let's analyze this task a little bit. So what we need to do is that for whatever read we get from our machine for the enzyme activity, we need to bifurcate into different scenario based on the value of the reads. So if the reads is between 20 and 80, which means it's not too high, not too low, we are safe. We don't need to do anything to the read. It reproduces the exact activity of your target enzyme. And if the reads is too low, say for example below 20, then we need to do some correction to the reads by multiplying a factor of 1.25 to it. Similarly, if the reads is above 80, we also need to do some correction, and the correction is different from when the reads is below 20. We need to multiply a factor of 0.8 to the read. Then how can we implement this flow control in R? So notice that we are already beginning to control the flow of our code. So based on what you give the code, it should separate it into three different flows, below 20, between 20 and 80, and up higher than 80. So let's first don't do that so complex flow control. Let's just see the simplest flow control you can have. So in this case, we give a read to correct, and we store the value in this variable as we learned yesterday. And then we do something called if the read to correct is smaller than 20, then we modify the read to correct by multiplying 1.25 to it. So the only thing you didn't learn yesterday in these codes are first the keyword if, and then the round bracket and the curly bracket. So so it works like this. So the if is a keyword reserved in R. So as a revisit, as a reminder, that means you cannot have a variable whose name is if, because it's a reserved keyword in R. Once R sees this reserved keyword, it knows you are going to begin a flow control based on the condition, which is included between this round bracket. And here our condition is the read to correct variable is smaller than 20. And then, like, once you tell the condition at which you bifurcate the flow, then you tell R what to do if read to correct is smaller than 20. What to do is included between the curly bracket here. So it's just my personal habit of having the curly bracket in two separate lines. If you prefer, the curly bracket can also be here, but it must include all the things you want R to do once the correct condition is met. Then in our real application, we want 3 different flows. So we can do this by combining if with the else if and else keyword. So here is, first, this is this part, the line 9 to 11 is the one we have already seen in the previous slides. Then to add another condition saying that if the read is larger than 80, so then we correct the reads by multiplying 0.8 to it. And finally, we add something called else, and then say this read does not need correction. So what really happens in R is R first start from line 9, says, oh, is the read to correct smaller than 20? If it is, then it immediately do what it is inside the curly bracket between line 10 and line 12. But what if the read to correct is not smaller than 20? Then R begin to look at line 12 where the else if is. So if R find the first condition is not met, then it begin to look to the closest else if and find, oh, now R begin to think whether the read to correct is larger than 80. And again, if it is larger than 80, then it immediately does what is asked to do in the curly bracket immediately following the else if. Yeah, and then if the read to correct is larger than 80, is not larger than 80, then finally it goes to the else where it prints nothing needs correction. Okay.
Do you need to go to the next line after your if statement? So like if, and then you start your curly bracket on line 10, or can you start your curly bracket on line 9 if you want?
Okay, so he's asking whether you can put a curly bracket here and on the same line. Yes, you can. This can be useful if if what you want the if to do is very small, is very short, like in our case. But if you put everything here, like you end up will have a very, very long line, which is very difficult to read. So that's why typically people change to a new line when they start the curly bracket. So yeah, it's all for readability. If you want, you can put everything on the same line, but it will be super difficult for you to read and write. Yeah. I think get some chat. Sorry. Oh, okay. Don't worry. Okay, so you see we are doing lots of comparisons in the round bracket, which is here. So you must be wondering, like, what are all the comparison you can do in R? So I list like almost all of them here. So like A is bigger than B, like I think all these perhaps the bigger than or equal to, smaller than or smaller than equal to is quite intuitive. The first a little bit non-intuitive one is, what if you want to check whether A is not equal to B? So you use the exclamation sign followed by equal sign to tell R that I want to check whether A is not equal to B. It's just like there is because there is nothing on your keyboard reads this, the classical not equal to sign. So that we need to use the exclamation mark plus equal to tell R that, oh, we want to do a not equal comparison. And then the second non-intuitive and very frequently tip over novels is what if you want to check whether A is equal to B. Here you need to use two equal sign. I will emphasize again, two equal sign, not one equal sign, because as we have learned yesterday, one equal sign means assignment rather than whether it is equal to. This is the one equal sign is equivalent to the arrow sign you frequently see throughout this class. It means assign the whatever is in B to A rather than whether A is equal to B. And the most tricky thing is that even if you put if A one equal sign B in the round bracket here, R will not give you any error. So similar to many other programming language, because the assignment, once the assignment is successful, it thinks it's something like a true, so it will go through. But it never checks whether A is equal to B. It just do an assignment and goes through. So be very careful about this. So whenever you want to check something is equal to B, you use double equal sign rather than single equal sign. Okay.
If you had two if statements in something like an if and else if type thing, and both the if statements are true, does R look at only the first if, or does it look at both ifs?
Okay, so he is asking something, say for example, if I do if read to correct smaller than 20, and then for whatever reason here, I put if, again, else if read to correct also something like smaller to 20.
Let's say smaller than 20.
Yeah, so what R does is that once the first line is good, then it just does whatever it does to do and stop looking at anything following it. So it will only evaluate. So it check the condition from the top to bottom. And once the condition is met, it exaggerates whatever it should do and then stop. So it will never see like the second one, you put it here.
So if statements are not mutually exclusive.
That's a kind of very mathematical way of saying that, yes. So only when else if, only when the first condition is not met, then we'll look at the second condition, because that's what it means by else if, right? Else if, yeah. I'll just need to check. Okay, no, nothing from the. Yeah, well, thanks for bringing that up. So that's a very good point. Okay, so at this point, let's have a revisit to the logical data type we talked on our first day. So what really happens between the statement if read to correct smaller than 20 is that R first evaluates read to correct smaller than 20 to see whether this is true or false. So it first evaluates this statement and then returns a logical data type of either true or false. You may also see some people refer to this as Boolean. So they two are equivalent in R, so logical or Boolean. Yeah, just whenever you see logical or Boolean appear in these slides or elsewhere, it means the same thing in R. So then the if statement does what asks it to do in a curly bracket if it sees true and skips it if it sees false. So all in all, it means what if condition is looking for is not a comparison. As long as you give it a true or false logical value, it will be happy with it, which means you can even make your comparison elsewhere in your code and just pass the results to the if, and it will still work perfectly fine. So similar to numerical type, we can also do some operation on logical or Boolean data type. So here are the ones you can do to them. You can do AND. So A and B means it will only be true if both A and B are true. If both of them or either of them is false, then A and B will become false. A or B means as long as one of them is true, then the whole thing is true. It is false unless both of them are false. And finally, you have a not operator, which means not true is false, not false is true. So you just inverse the true and false with the not operator. So with the operator, we can do something like this. Say, for example, instead of jumping to correct our reads, let's first create a code for judging whether our reads need to be correct or not. Say, for example, we have a read to correct equal to 30, and then we check if read to correct is smaller than 20 or read to correct is larger than 80, then we print this read needs correction. And if not, then we print this read does not need correction. So to expand a little bit more, so what really happens in this in the round bracket after if is that R first evaluates read to correct, is it smaller than 20? So in our case, because 30 is not smaller than 20, so it returns false. And then R evaluates, is read to correct larger than 80? Also false. And then R evaluates false or false. It's still false. And if C is false, so it skips this immediate instruction below it and do whatever it is told to do in the else, which is print this read does not need correction. So here is the exercise. So before in the slides you have already seen, so we do the judgment based on the or operator. So just have 10 or 20 seconds, think on your own. What if we want to rewrite the code, but this time we only use the AND operator, not the OR operator? Yeah, you don't need to physically write the code down, just have a quick thoughts about how you are going to write it. So here is how we're going to do it. So all the stuff happens in the round bracket. So now instead of asking whether it's smaller than 20 or larger than 80, instead we say if the read is larger than or equal to 20 and the read is smaller than 80, then we print this read does not need correction, which means now we check whether the read falls in the safe region rather than whether it falls into the needs to correct region. So you need to also inverse the order of what to print. So if the if condition is true, this time we print it does not need correction. And if the if condition is false, then we print this read needs correction. Okay, so now we learn how to handle like our reads based on its values into different flows. Now another thing we need to do is we need to scale up because we can have hundreds of reads waiting for us to correct, and you definitely don't want to manually apply the if statement to them one by one because it's going to be super tedious. So therefore, we can use another tool in the flow control in R, which is the loop. So what loop does is it allows you to loop through a very large data based on the loop condition you specify and do whatever you specify it to do during each loop. So it might be a little bit abstractive here, but we can, sorry. So let's see a specific example. So let's say here I have a vector storing like something like 7 reads. And now let's start from the simplest thing. We just loop through it and print them out one by one. So again, similar to if, but this time we start with the keyword for. And then following with the round bracket again. In this round bracket, we specify the range we want to loop through. So here we say we want to loop through number 1 to 7, and the iRead variable here will hold the index to loop through at each loop. So what happens is that at loop 1, R gives 1 to iRead, and then we print the reads to correct followed by the square bracket of iRead, which means iRead is 1 now, and we get the first element out of the vector. And then during the second loop, R assigns number 2 to iRead. So now we can, during the second loop, we can print out the second element in the vector. And it keeps working like this until iRead is 7. And R finds that, oh, I have already gone through all the range that the user tell me, and the for loop just stops. And the output will look like this. So you print out each value in the vector one by one after you go through this for loop. So what we can, and another way of doing loop is something called while loop. So in a while loop, what we do is something like this. Instead of using the for statements to give R a range to loop through, this time we use the while keyword and give R a condition where it should loop. So in our case, say for example, we say we first set iRead equals to 1 as a variable out of the loop. Then we use the while to tell the R to loop until iRead is larger than 7. Or in other words, to keep looping while iRead is smaller than or equal to 7. And then within the while loop, in addition to print out the reads value we want, we also change the iRead such that each time iRead increase by 1, and thus during the next loop, it will bring out the next element. So in a while, so just to illustrate the difference, in a for loop, you give R the range you want to loop through, but in the while loop, you give R a condition where R should keep looping, and it is your own business to make sure like this condition can be met. So the reason why I say this is that be careful about what is so-called a dead loop. So let's in this part of the code, I just comment out the line of the code to increase the read by 1 in the while loop. So because it's commented, so R will ignore it, thinking that it's something intended for human to read rather than for R to read. So what happens is now iRead is always 1 because it never gets increased. And as a result, it will never be larger than 7. The result is that R will keep looping. And during every loop, it says, oh, our iRead is 1 smaller than 7. So it will keep looping, and forever. And when you do this, R will focus itself 100% on the loop. You cannot do anything else with R because it thinks this loop is not finished yet. So how to use, like, to be honest, it would be quite common, like, especially at the beginning, that you forgot to change the condition of the loop such that it never exists. So in this case, if you look at whenever you find yourself in this dangerous situation, so you can find there is something look like a stop sign on the lower left part. Actually, it should be somewhere in the lower middle of the RStudio interface. And it's essentially where the console is. So you just hit this stop button. So RStudio will immediately tell R to stop whatever it is doing. And thus you can save yourself from the endless loop to make some change to the loop and run it again. So as you can see, like, maybe your first intuition is that, the for loop seems much more convenient. I just give it a range. I don't need to worry about it never ends, because as long as the range is ended, that's fine. But in real practice, sometimes while can be the while loop can be very convenient in a case where you are not quite sure where the loop should stops. Say, for example, here, we imagine a scenario where we want to print the reads until we reach a read that is larger than 50. So if I just give you a random super long vector, it will be quite difficult for you to figure out who is the first element that's bigger than 50. And then if you cannot find who is the element bigger than 50, you cannot specify a range, so you cannot use for loop. So here, what we can do is we can use a while loop to achieve this by including whether the reads to correct is smaller than 50 inside the while condition. So in this case, when the R is looping through all the elements in the vector, it checks whether this current read is larger or smaller than 50. And if it's larger than 50, it stops the loop. And then you don't need to worry about where this element is, because the loop will automatically stop at this element. So all in all, it means just choose between for loop and while loop based on your own needs. In while loop, it's a little bit dangerous, because if you forget this, the I read equals to I read plus 1, you are going to the dead loop. But anyway, you know how to save yourself from the dead loop, so it should be not that horrible. Now let's see something about how we can make our loop even smarter by combining it with function. So in the previous for loop I show you, you need to manually specify like 7, which is the length of the vector you want it to loop through. So let's say next time I give you a super long vector, like, then you need to change this 7 to something else. How to be lazy, like, whatever, can we have a for loop capable of handling like vector of any length without the need to change anything to it? So there is. So what we can do is that we replace this 7 here to the output of a function whose name is length. So as you may have already, like, you can like easily guess that the length function just take a vector and it returns the length of the vector as the output. So when R sees this, so it first evaluates this function and it returns you a numerical number corresponds to the length of the vector you give to it. And then R use this to specify the region to loop through. So for no matter vector you give to it, R will always be able to handle it without the need for you to specify who is here. So in addition to this, like currently what we are doing is we are always loop in a way where there is a step increase of 1, like in each loop. Say, for example, from 1 to 7, it's always 1, 2, 3, 4, 5, 6, 7. And actually we have the freedom to even jump like at any like order we want. So because in this for statement, the I semicolon 7 is not something like a keyword that the for loop is looking for. It's just a convenient way of creating a vector from 1 to 7 with a step increase of 1. So it's equivalent to C 1, 2, 3, 4, 5, 6, 7. So what this means is that similar to if is only looking for some logical values you give, for is all just looking for some numbers you give it to loop through. So what you can do is that you can just define something like a white list. Say, for example, in our data, we always, like we occasionally will have some data we know that's corrupted and we don't want to analyze anyway. So we define something like a white list telling R that, oh, only do these, only do like the elements 1, 3, 4, 6 in a vector for me because I'm only interested in this. And then you can, sorry?
Is there an option, let's say your vector is like 500 elements, and then you say, I want to do everything except say number 236.
So in this case, the first thing comes into my mind is you create from 1 to 500 a vector and then delete whatever is equal to the. So essentially, in this case, you define a black list and then take the intersect out. So there are functions doing that. So yeah. So to those on Zoom, so one of the students is asking, instead of a white list where you want the for loop to visit, can you define a black list where you just don't want the for loop to visit? So first, for loop only takes something you want it to visit. So the way to create something like a black list is that for the for loop is that you first define the whole range, then you subtract what you don't want from it, and then give the final like subtracted range to for loop, asking it to loop through it for you. So there are also functions that can help you do that. We will not cover it here, but you can easily search this on ChatGPT. Yeah, if you want, if you are in that situation. So some even more advanced application is that for loop, in addition to a vector, it can also accept something like a list. So say, for example, here, we just want to print some, like go through a list of random stuff that's either numeric or character. Again, just put it after the in argument and R will comfortably handle it for you. So now that we have learned the if statement to handle to give different treatment to our data based on certain conditions, we have also learned how to use loops to loop through lots of reads and do something to them. So now what we can do is to combine them together, which means we are ready to jump back to this question of solving this problem of how to crack the reads from a machine that's too old. So I will just give you a few seconds, like based on what you have learned in the past several like tens of minutes, think about how you will solve this problem. So now you have all the tools you need. Think about how you will write the code. Okay, so let's look at this large chunks of code. So first, we begin from line 91. Just the exact line number doesn't matter. It's just easy for me to refer to where I want you to look at. So at line 91, so we just define the reads we need to correct, nothing fancy, what we learned yesterday. And in line 92, you see some new friends, rep. So in this, in line 92, so what I did is I create an empty vector for holding the corrected reads is the name of the variable indicate. So the idea is here. So you can always directly apply the change to the original variable, like the reads to correct in the line 91. But it is really a good practice to keep the raw data for future reference. Or in the future, you want to do something else to the raw data, you still want to keep it. So instead of overwriting it, it is sometimes more preferable to have us to store the manipulated or corrected reads in a separate variable. So that's what I'm doing here. So I just create a home for our corrected reads. And because at this point, we still have no idea about the exact value of the corrected reads. So I set all of them to be NA. NA is another keyword in R, meaning not available. So, and then because I have multiple reads to correct, I just use the rep function, means repeat. So it means repeat the keyword not available for n times, where n equals to the length of the reads to correct. So if I have 7 reads to correct, here I create a vector all containing 7 not available. So this is the new home for our corrected reads. And then we are going to use our for loop to fill in the corrected reads into this variable. So then in line 93, you see like our smart for loop, which can always handle reads of vector of any length. Then within each for loop, we put the if statement we have seen before, judging whether the reads from reads to correct is smaller than 20 or larger than 80 or nothing, or like small, or in the range between 80 and 20. And at each condition, we apply the corresponding correction factor to it, or simply do nothing by just parsing the original reads to correct into the corrected reads when it doesn't need to do any correction. And finally, we can, of course, show our corrected reads by print this vector at line 106. So that's how essentially how we solve this problem, like by combining for loop and the if statement. Just let me check whether any. Yeah, perfect. No problem. Okay. Then, you know, the like good things always spread really fast. So your lab mates heard that you now get a function. You now get some codes that can magically correct the old machine and save the lab like 10K money to buy a new machine. So, and given that other people are also like measuring those activities using that old machine, so they just want to get your codes to correct their reads to ensure they also get a 100% correct data. However, when you show all those like loop and if to them, they are overwhelmed by the complexity. They say, oh, I'm never going to learn how to use such a complicated code. And they say like, they say perhaps they also take section 3.1 yesterday. So they ask you like, can you just give me a function that only one line, I specify the input and boom, I get the output that's corrected. So of course, you can do that. So let's revisit what we learned yesterday about function. So yesterday, I only told you that there is some magic in the black box. I only tell you like what input you should give to the function, but I never tell you what's really inside the function. So like currently, we only use the built-in function provided to us in R, all those like matrix, rep, or length. In fact, so these functions are not just grow out of nowhere. So they are just some lines of code telling them what to do. And if we need to copy and paste, say, for example, our read correction codes to multiple people, it can be quite annoying, right? It's not that short. And if we need to use it elsewhere in another code, then we keep large chunk of codes, like keep copying and pasting. It's very annoying. So how about we package our codes into a function? So the next time anyone else want to use it, we just call the function's name, and then that's all done. So that's the essential idea why we are allowed to define our own function in R based on whatever we want. So it looks like this. So very interestingly, define a function is like using a function. So first, you call a function whose name is function, which means create a function. So here, as the argument of the function, so you put in the name, the variable you want to refer to as the input. So keep in mind, this reads to correct just means in all the following codes telling you what the function to do, you are using reads to correct to refer to this input. Sorry.
So on your line 105 function, you must have that function keyword, and what
Yeah,
you're saying
that-
is
that-
correct underscore reads is your like the name of your function, and then the reads to correct is your what you're putting into the function.
Yeah, you just say what I'm planning to say. Yeah. But yeah, don't worry, I will talk about this again. So the reads to correct is how you want to refer to the input in the following code. It doesn't mean the reader must pass a variable whose name is reads to correct to the function. This is very important. So reads to correct is just like a placeholder here for you to refer to whatever the reader passed as the first argument. Because when writing the code, you want something to you want a variable name to refer to the first argument, and the name is reads to correct. The user can pass whatever variable with whatever name as the first argument, like reads, ABC. Anyway, it's treated as the first argument. Yeah. And then for the arrow sign of assignment, you assign to a variable, something like a variable, but now this variable becomes your function. So you can call it later, call this function later by using this variable's name. So you can think it as a variable holding your function. And then within the curly bracket, we essentially copy in what we have done before. That's the large chunk of code we use to loop through all the vectors and then correct each reads. The only difference is we add an extra line here at line 121 saying return corrected reads. So this means we return the, please note, this is corrected reads, not correct reads. So corrected reads is referring to the variable we create at line 107. Yeah, I just realized I happen to make the function name very similar to a name of the variable in the function, but they two are completely different from the point of view of R. I just don't want you to misunderstand like this, just keep in mind the extra difference of the ED after correct. So what it says is that the return means asking the function to return the corrected reads variable created within the function as the output of the function. Because we have learned all functions give you some sorts of output. And here is how you specify what the output is. Like, for example, you don't want to return something like I read because it's kind of useless. No user wants to see how it works within your function. What users care about is the corrected reads, and that's why you can return only this variable by using the return function. And another thing I need to emphasize is that once the function returns, it immediately ends. So return is also used by the function to tell whether it should stop. even if you put lots of codes after return, nothing will happen because the function ends itself the first time it meets the function return. So,
Question.
mhm,
So line 124, they're calling the function,
uh-huh.
right? So you have to assign the variable corrected reads is assigned to then the function correct reads that accepts that vector as an argument.
Yeah.
Okay, the fact that they assigned it corrected reads and you named it corrected reads on line like whatever up there,
Mhm.
that's a coincidence, or it has to be that way? They have to know that they need to assign that.
Oh, yeah.
Use the
So,
function that
so
way.
you are asking this correct reads need in 124 needs to match this one. Yeah. So it must match. So
Okay.
by here in line 105, you can think you are just giving the function a name. And you must exactly match the function's name when you want to call it.
Right, but you're calling the function like correct reads there. I thought corrected reads was a variable.
Here I'm calling correct reads.
Yeah, that's the function name, right?
Yeah, that's the function name, which is here.
Right, so you can't call the function by just saying correct reads and then the argument. You have to have that first part of it where it says corrected reads is assigned to correct reads.
Oh, yeah. So, okay. So from line 105 all the way to line 120 is called the definition of the function. Because R doesn't have built-in correct reads, and when you want to create a customized function, you must tell R how this function looks like. So this is from line 105 to line 120. This is how you define the function.
Right.
You define it, and then you only need to run this definition once. So as long as you run this definition once, R is not aware that there is a function whose name is correct reads and do all the stuff in a curly bracket. Now you can call it for whatever number of times you want by referring to the name.
Yeah, I
correct
don't think
reads.
you understand what my question is, but I'll just ask you in the break.
Oh, okay, sorry for that.
That's okay.
Yeah. So, yeah, let me see there. Okay, so the Zoom seems to be quite quiet. So, yeah. So anyway, so the flow of logic is that you first define a function, then you run this chunk of code from 105 to 120 once, which means the function is defined. Then from now on, you can always call the function based on its name and pass different input you want to put into it, and it will return the output as you defined in the definition of the function. Yeah. So, and as you can see, it's very convenient because you only need to do it once, then you can use it for multiple times without the need to rewrite all these codes. And to make things even more convenient, you can simply define your function in a separate R script, which means that script is just the place where you hold all the codes. So that script only holds the definition of the function. And then you distribute the script to whoever you want. And when they want to use it, they just use the name source and then plus the full path to the script holding the function. And with this one line, they immediately define the function, and then they can now use that function. So for here, I just to make it different from the previous sum function, I just make it a random name at shareable, which means much easier to share. So now you don't, like in the previous definition, like you still need to ask anyone who want to use your function to copy all of these codes into their script and run it, and then do it. And you don't know like how are you going to pass it to, like, is this through email or whatsoever, like how they come to copy and paste it. But now in the second scenario, you only need to give the script to whoever want to use it. And they only need to refer to it once by using the source function, and then they can keep using the function. So as a conclusion for section 3, so we first learn in section 3.1 how to find and use functions. And then today we learn in section 3.2 how to use flow control, like to make our codes no longer flow just like a very boring linear fashion. Instead, we can have loops and bifurcations and all those kind of stuff. Then finally, what I've shown is how we can combine the built-in functions available in R together with other flow control components to make our own functions or our own analysis pipeline. So this is essentially what you will be doing every day when you begin to use R to analyze the data. You combine function with flow control, and then you do all sorts of stuff you want. Where do you find all those functions? Ask AI, read the technical documents. Or where do you find flow control? You just learn it's if, for, and while. Not that difficult to remember, right? Yeah, only 3 of them, and it's enough for you to do tons of interesting stuff. So we will have a pause here, so like 10 minutes rest. So go to the restroom or whatever. Yeah. What's the?
Here, just put the slide back.
Yeah.
Okay, so this line here,
Uh-huh.
someone who wants to use this function is defining a variable corrected reads,
Mhm.
and they're assigning it to the function to this argument,
Mhm.
and this is getting passed to the function,
Mhm.
and then we're gonna print that out.
Uh-huh.
So my question is, could I have called this like my data?
Definitely.
Okay, because you named it the same thing as there
Oh.
as there. And so I wasn't sure whether I needed to know that to do this.
No,
part
no,
of
no.
it. I could just say like my data correct reads, blah, blah, blah.
Yeah, this is
Okay.
my fault. So this is so this deals with some more complex, more advanced concept of scope of the variable within the code. So this one, this corrected reads only within
Applies to
this
the function. Okay.
So it's only used to refer to the output within
yeah.
the function.
Yeah. Okay.
So once you
Because
apply
what my
this,
question was, is like, how would, if I'm only just using the function as a black box,
Oh,
I
yeah,
wouldn't
yeah.
know what that is
Yeah, yeah,
to
yeah.
call it
so
there.
it just
But I could just say like my data.
yeah,
and-
you can
and
say
just-
my data
okay.
here output.
Alright, so I just
whatsoever.
need to know the function name and a vector.
It's my mistake. Just
Okay, that's
my
cool.
brain is kind of
No, I get it, but I just
then notice.
wanted to be sure.
Yeah, I will class. I need to clarify this to other. I think other people might also get confused. Yeah. Yeah. So I think we can just intro to R. Yeah. Find your name and maybe on the second. No, I see my name, but should I use a pen? Oh yeah. So yeah. I was here yesterday on Zoom. Is that? Yeah, just talk to just and where should I send it? Just right here? Sorry, what? Should I send it like just right here? I don't think you need to sign this tick. Yeah, it's fine, but yeah. Great. Yeah, I think we can begin again. So so during the rest, one of the students clarified a question she has in mind to me, and this made me realize that perhaps we should revisit this part of the definition of the function again, because I made a confusion. I write the code in a confusing way, where the corrected reads the variable here on the line 1 to 4 has exactly the same name of the output to return in line 1 to 1. So first of all, the name of these two doesn't need to be the same. So feel free to use whatever variable name you want at line 1 to 4 to hold the output from the function. It can be my data, my corrected reads, or whatever you want. And having said that, I also realized that although at first I tried to not touch the concept of the scope where a variable can live in this course, because I think it adds some level of complexity and confusion to this class, which is an introductory one. But during a second thought, during the break, I think maybe just to give you guys a taste of the scope of the variable. If you find it even more confusing, fine, just forget about it. But if you find it answer your question, then that's good. So during the definition of the function, you can see we create several variables. Say, for example, reads to correct here, corrected reads, which is here, and I read. So for all those functions, like in this round bracket and the curly bracket, they kind of have a scope where they live in, which is limited to the definition of this function, which means these functions will only be used within the function we define. But outside this function, when we are writing other codes not related to calling this function, they do not exist. This means you don't need to worry about, oh, since I define a variable called read to correct here, should I avoid to use the same name in the remaining part of my codes? The answer is no, you do not need to, because all these variables you see here from line 105 to line 122, except the function name itself, only lives in the definition of the function. So they are only there to help you define the function. And once the definition of the function finishes, all those variables, they disappear and become recycled. So you can feel free to use them in the remaining parts of your code. That's it. I hope I do not add extra level of confusion, but if you feel that you are confused, just forget about it. And keep in mind that you don't need to have the exact same variable name as the return to get the output. You also don't need to have the same name of the variable used here as input. That's all.
So when you say to repeat the loop in the line 147, will I always need to write repeat NaN always? Or do I need to specify a number?
Oh, so for the repeat function, the first argument is whatever you want it to repeat. It can be NaN, which means you create something empty. Everything is not available. Oh, sorry, I think here I have made a typo. I should use NA.
NA.
Yeah, NA.
Okay.
So NaN means not a number. So it's slightly different from NA, but doesn't affect the code function here, but it's just a typo. So you can put NA, or 1 or 2 or 3, depending on how you want to use the rep. So the NaN or NA is not a fixed component here. Yeah. Put whatever you want it to repeat. We will soon see another example of using rep.
Okay.
Yeah, sorry, that's a mistake. So now let's move on to section 4. That is standing on the shoulder of giants. this is going to be a very important part of how you will use R in the future, which is how to install and use packages from other people. So what we have seen is that the built-in functions available in the base R, like when you download it, might not be enough for solving lots of like data analysis tasks. So you see, we just, to correct the reads from a machine, we create our own function. So similar to this, so experts in various kinds of fields who are using R also create their own functions when they're trying to tackle their own problems. And if they find, oh, this problem actually is quite common across the whole fields, one thing they can do is that they can share, they can package all those customized functions they write into something called a package and share it with every R users all over the world. So this leads to the concept of a package. And as an example, we can install a package called tidyverse. I'm not asking you to install it now on your computer, but yeah. So some brief words about tidyverse, because in addition to installing it here, so the remaining part of the class will spend lots of time on teaching you how to use this package. So what's so special about this package that I decide to teach you guys about this specific one is for two reasons. So first, tidyverse itself, I think it's, I'm just guessing. The name is from the Marvel universe or whatever verse, because you have several superheroes in the Marvel universe. And in tidyverse, you have several superhero packages for you to handle the different fields of the data analysis. So tidyverse is a collection of different packages that helps you to process your data, analyze your data, clean your data, and visualize your data. So it's a very general purpose tool that perhaps like everyone in this class will more or less need to use part of the tidyverse. So that's why I think like it's worth to teach you guys this, because you guys are highly likely need to use this. And the second reason is that tidyverse is a very good role model to learn from. So I can only teach you R for 9 hours. And then you need to begin to learn from someone else. Tidyverse, how the library, how this package is designed, how the function is named, and how it accepts different arguments is a very good role model to you. Like what can be a good function? You will find many functions in tidyverse. They are very precise, but at the same time, also very versatile, which means you don't have to have 100 functions for 100 different purposes. Instead, one function in tidyverse can solve lots of problems, but at the same time, you wouldn't feel you are overwhelmed by this one single function, because when you want to use part of it, it's always very intuitive. So that's why I think tidyverse is really a good starting point. You can learn from it and you can benefit from it. So whenever you want to install a package, usually you go to the website for an instruction. So typically you will get a one-line instruction here telling you, oh, if you want to install tidyverse, please just run this code in your R, and then you will see some horrible stuff like this. So yeah, don't worry, it's not your computer is going to explode or whatsoever. So it's just, it begins to download all the necessary components, the tidyverse or the library you want to install from. Sorry.
So like, if I want to install, I just type whatever they said there onto where my R Studio is and then hit run or something.
Yeah, or you can directly type it into the R console and hit the enter.
Right.
Yeah, so you just type install.packages, which is R's built-in function for install packages. And then the name of the library separate are like surrounded by double quotes. And then it will begin to immediately, you see those red text and black text jumping out. It's just R is trying to collect these packages from the internet and then install it and make it work for you locally on your computer. So don't worry, you will see tons of red text like this, and it's nothing wrong. Yeah. Then you must have a question in your mind is like, where is the package from? So it's from somewhere called CRAN, which is Comprehensive Archive Network. So currently, so it's a network for, you can think it's just a website for collecting all the packages people want to share with other people. And currently, as I check when I was preparing these slides, there are 22,878 packages collected at CRAN. I should warn you that each package contains multiple functions. So the real number of functions you can use from all these packages would be an even bigger number. That's why I say from the right beginning, it's impossible to teach you all the possible functions in R. I mean, it's not even possible to teach you all the packages because there are over 20,000. And another thing that can make it even more complicated is that one package, instead of using those built-in functions already available in R, it can also use some functions from another package. This means a package can depend on another package, and that package can depend on another package. So one package has a very complex network that it's like, oh, to make this package work, I also need the other 3 packages. So CRAN is where the developers, they develop some tool to automatically track the mutual dependency between different packages, so that when you download one package from CRAN, they will automatically check, oh, are you missing the dependent packages? And if you are missing, they will automatically also download and install it for you. So it's all included, all these fancy function is just included within this one line install.packages. Yeah.
I need to check, do you have to hit download on the website first and then install?
No, there won't be any download sign on the website.
Oh, okay.
You just run this command.
Oh.
This command goes to whatever website is related, actually it's CRAN, and then pull down all the packages.
Right.
So there you wouldn't see any download sign on that on the website of the library you want to use. That's a very atypical way of downloading packages. And yeah, so to clarify the relationship between install.packages and CRAN is that install.packages get packaged from somewhere. And if you don't specify as an argument, then the default is CRAN. So this is the relationship between CRAN and install.packages. Again, similar to R, CRAN is completely free, even though it's very fanciful, it's completely free. So you don't need to pay for downloading any packages from it. And the thing is that although we already have CRAN for maintaining all those packages, biology is such a unique field. First, it's very big. And second, it speaks its own language. Perhaps no other field cares so much about the 4 letters A, T, C, and G. But in biology, it carries a very different meaning to encode the DNA. So people find that, researchers find that, oh, there are many packages specifically dedicated to biology or bioinformatics in R. So there is finally a spin-off from the CRAN network, which is another similar network called Bioconductor, specifically dedicated to maintaining packages for bioinformatics and biology. What does this mean to you is that sometimes if you want to install a package and that package is generally regarded, okay, yeah, I just think I forgot to start the recording, but turns out I stopped. Yeah, good. But that package happened to be considered as something related to biology, then very likely it's available on another network called called Bioconductor. And to download any package only available on bioconductor, you need to do two things. So first, you install a package called BioC Manager from CRAN. So this guy is available on CRAN. Then once you have the BioC Manager installed on your R, then you can call the install function within this package so as to install your biology-related packages. So here, for example, DSeq2 is for analyzing RNA-seq data. And very clearly, this is only related to biology. So it is only available. I'm not sure whether it is only available, but the most recommended way of downloading it is from bioconductor. So what you should do, as instructed on the website, you first install the package BioC Manager, and then use BioC Manager's install to download DSeq2. You only need to do this part once. So once you have the BioC Manager installed, you can ignore these two lines. Now we need to learn some, like let's assume we already have the packaging installed. So it's indeed installed on my PC. Then we need to learn how to use a package. So it turns out you cannot use it directly by assuming you already have it. You used to need a function to let R know that you want to use certain packaging. And that function is called library. So what you do is you put library and the package's name, and this time no double quote needed. Yeah, no double quote. So library BioC Manager or library tidyverse. That's all. And although this is the most common way of calling, like telling R that you are going to use a library, there is another way you can also use, which is the package's name followed by 2 semicolons and the function name you want to use. We have already seen it. Say, for example, BioC Manager 2 semicolon install means I want to use the install function from the package BioC Manager. So you may be wondering, like, okay, why do I already take like pains to install the package? Why do I even need to use these extra steps of like declaring like which library I want to use, or sorry, which package I want to use in R? And the reason is that it's the main reason behind this is because packages can conflict with each other. Say, for example, this package is written by one guy at UCLA. That package is written by another research group, say, for example, at Harvard or MIT. So it's impossible for all the people who are trying to develop a package to be aware of each other. So it's very frequent that one package can have a function whose name is exactly the same as another function in another package. This leads to the problem that if you try to load 2 packages at the same time, R will be confused. Like, say, for example, there is an install function in package A, and there is another install function in package B. And when you try to load both libraries by the library command, I will think, okay, when now you tell me you want to use both A and B package, but both of them has a function whose name is install. Then when you tell me to install, which function should I use? So R's way of handling it is whatever library is called later, which means whose library command line appears like later, it will overwrite the function in the previously loaded package. Of course, this is not something very easy to manage because now how you use R depends on what's the order you load each library into your R. So that's why we typically it is not recommended to brainlessly load all the packages you have into R. Instead, you are encouraged to load only the package you need for the current data analysis task. Say, for example, in this task, you only need tidyverse, then just load tidyverse, don't load other stuff. In that way, you need something else, then just load that one without loading tidyverse. And there is another way for you to get around this problem is that if some functions, you find that you only need it 1 or 2 times, not that frequently in your code, but you definitely need them, then you can use the package name to semicolon a way to call it. This is only limited to that function on that one line, on that line of code, which means when R sees this, instead of loading all the package into the R's environment, it only says, oh, for this specific function, let me go to this package to search for it. So it's a very neat way, although a little bit complicated if you tend to use a lot of packages, a lot of functions from that package. Then you see this package semicolon appear everywhere in your code, which can be a little bit tedious to type. So, but if you only need 1 or 2 functions from certain package, you can use this way to minimize the chance of crashing with other packages.
So the package ;:, function just means we will say we will load it for now and then we'll pretend it doesn't exist after we're done with this.
Exactly. So it only deals with this current line of code. And once it finishes, I'll forget about that package. Yeah. Oh, and one tiny thing, RStudio is very smart. So once you type package name to semicolon, it will and begin to roughly type a few letters, then all the functions name from that package matching your preliminary typing will pop up. So you don't even need to remember the exact name of the function in that package. Yeah. So to conclude for section 1 to 4, so I try to conclude them together because they form the cornerstone of any programming language you will use in the future. So, which means you get, this class is buy one, get multiple free. Even if in the future you say, oh, I need to pick up Python, I need to pick up MATLAB, you just walk through the same concept of section 1 to 4, and you can claim you are at least better than novice at that programming language. And let's just take a quick review of what each section is telling you. So section 1, we install R and RStudio, but more generally speaking, we talk about the relationship between programming language and integrated development environment. Similar to other programming language, you first download the programming language itself for interpreting the code and do the job. Then you decide which IDE you want to use. Say, for example, Python has tons of different IDEs. Just pick the one you really like. Like some people like the interface to be like very fancy. You can put your favorite image at the background and write the code. Some people like to highlight different part of the code, like very colorful, like purple, green, or whatsoever. Pick whatever you like. Yeah, and they don't affect anything about how the programming language really interpret your code. Yeah. Section 2, we discuss about how to put data into R. And more generally speaking, it's about data types and data structures. It exists everywhere in every programming language, such that in the future, if you take a computer science class, perhaps you will have a class specifically discuss about data structures without the context of a specific programming language, because it's a universal concept, exists everywhere in programming. You may find the exact name or type of the data type and data structure is a little bit different. Say, for example, in some programming language, in addition to character, you will also have string, and a string and a character is not equivalent. Or in other programming language, you will have some other stuff, I don't know. but it doesn't jump out the concept of data type and data structure, which means the second thing you do when you try to learn a programming language is just figure out who are the basic data types and data structure in that programming language. Then the third thing, because for most of us, we are using the programming language for analyze data. So we jump to section 3 for learn how to use functions and flow controls to with the focus on how to use that to manipulate and analyze our data. But of course, if you want to earn something like a 6-figure salary by joining the software development industry, section 3 is still applicable. You just learn it how to do software engineering with flow control and yeah. And finally, you learn once you feel you are comfortable with section 1 to 3, then you begin to establish your kingdom of toolboxes to use for analyzing the data by install packages such that you do not reinvent the wheel by trying to designing a function that people have already designed for you. So yeah, you can pick up any programming language by sticking the concepts in section 1 to 4. For me, I pick up MATLAB first, and then I apply all this stuff to R, and that's how I learn R. Yeah. Okay, now let's truly jump to something that's specific for R. I mean, that's because this course is introduction to R and data visualization. I'm just afraid that some people will complain to the manager that, oh, this guy claimed to teach this course, but he didn't teach anything specifically related to R. Okay, so for all those people, here, tidyverse, something you can only find in R, so it's here. From now on, we are specifically focused on this package, a very powerful one that only exists for R. So as I have mentioned before, just like the Marvel universe, you have, so Batman is not in Marvel universe, right? You have Iron Man. Sorry, I forgot. I'm very familiar with. Anyway, you have lots of superheroes in the Marvel universe. Similarly, in Tidyverse, you have superheroes for helping you conquering all those giant monsters of data. So we have within Tidyverse, we have readR, a package dedicated for reading external data into R. We have dplyr and tidyr for like once you read the data into it, how do you reshape and modify it to fit your specific purpose? And then we have ggplot2, which we will spend lots of time on it, for visualize your data with graphs. And we have something called per for something called vectorization, which is a useful tool if you want to replace loops. We will soon see what does this mean by vectorization. And then we will also have 4 other libraries dedicated to a specific type of data structures in R to reimagine or modify these data structures to make them more easy to use. So the general idea about tidyverse is that some data analysts, after using R, think some of the functions in R is not handy enough. So they rebuild all these functions and put them into tidyverse. So you may find for many functions we learn, you can easily find a similar function in base R, which is also doing something very similar. So if you want, you can also use it, but I can tell you, so tidyverse, based on the general community who are using R, the function from them seem to be even more like convenient and easy to use. Yeah, so that's the idea behind. And to guide us through all the section 5, all the huge section 5 of using how to use tidyverse, we will focus on a specific like problem perhaps you will more or less encounter in the future lab. So, but anyway, I make it up, so don't take it seriously. The data is I just put some random noise into some random numbers to generate the data. So it's fake. It's not from real experimental system, but do expect the real world is even tougher and even noisier. So one of your lab mates, both, so he's an expert in experimental biology. So he outlined a novel way of CRISPR screen and identified an orphan gene. So for those of you who do not know, like what an orphan gene is, so we have more than 20,000 genes in human body. And some of the genes are like superstar, like say, for example, RAS. That gene is, the mutation to RAS is known to cause a variety types of cancer. So that's why this guy is a superstar. Like there are lots of research groups all over the world trying to study this single gene. Like what's its promoter, like what's its sequence, can it be methylated, or like, and when it's expressed into a protein, like what's the structure of the protein, what inhibitors and activators can we find for that protein? So they are superstars, welcome everywhere. And at the same time, in the shadow of superstars, we also have those unknown orphan genes. So they are usually genes that has been only studied like by a few groups or even no one. So up to this point, no one even know what they are doing in our body. And to make things even worse, because no one knows what they are doing, then no people are willing to study them because it's not even a starting point. So CRISPR screen system enable us to scale, like to screen the function of each gene at a whole genome level, which means we are not missing everyone out. So this is bring some light to the study of orphan genes, because now we can run a screen at a much larger scale and recover some phenotype that's perhaps only related to that orphan gene. And this gives us a starting point, or at least some incentive to study that gene. So say, for example, your colleague Bob, he found that an orphan gene actually encodes an enzyme. And this enzyme, of course, because it's an orphan gene, has never been studied before. So there is no commercially available inhibitor and activator of this enzyme. But at the same time, it seems to be very important because it's related to the progression of brain cancer, one of the most deadly type of cancer in the world. So an orphan gene that's related to an important human disease that smells like a Nature or Science paper, something like that. So yeah, and of course your supervisor is super excited at that, but at the same time, how can you study this gene without even having some inhibitor and activator of this enzyme? Yeah, right. It's very difficult because you cannot perturb the activity of this enzyme to study how the biological system respond towards it. So given that you are now the expert in measuring the enzyme activity in your lab, so your supervisor assigned a job to you. So he asked you to screen a library of 200 different drugs to see whether any of them will happen to be an inhibitor or activator of that enzyme. So just to assure you, this is not some approach I make up simply for teaching this course. It's a very common approach. So you can easily buy drug library, which means it contains lots of small chemical compounds with different structures. And you can give each of the small compound to the system, to the target, to see whether the activity changes or not. And most of our drugs using nowadays, they are actually discovered in such kind of random non-targeted screen approach. It's not a chemist just sitting there and saying, this structure may work, so let's synthesize this out. And so people are trying to work in this way, but over the past few centuries, it always fails. And currently, AI is the next hope that finally we can design a drug rather than screen out a drug. But at this moment, still, if you have an orphan gene and you are looking for inhibitor and activator, still the most promising approach is still screen a drug compound library. And it's really not as small as 200. It's something like 2,000 or 20,000. Yeah. So luckily, your neighboring lab generously allow you to use their automated high throughput reader, meaning that they have liquid handling robots to take one drug, apply it to your sample, and then measure the activity. So you don't need to do it one by one on your own. And then, of course, replicate is very important. So for control, which means you add no drug, and for each drug, which means you add one drug from the library to your enzyme, you collect 3 replicates. So in total, you have 603 reads in total. And then the technician for operating that machine just export the data as something called drug screen.csv. He told you that all the reads are there, but life is always tough. He told you that for whatever mysterious reason, some of the reads are failed, like the machine just clogged. And luckily, the machine at least let you know where it fails by put a keyword failure instead of a numerical value of that read. So this is the problem set. So throughout section 5, we will work on this data set. First, we process it, analyze it, and finally, we visualize all the results to present to your boss or, sorry.
Just so I'm understanding this right, when you said that the 603 reads, some of them failed, does that mean that the instrument did not take that measurement, or that it failed because like it took the measurement and then somehow it just like threw away the data?
Oh, it can be both.
Oh,
I mean, this is not the focus of this class first, like how the machine fails, but sometimes it just like a bubble blocks the light path, so it cannot take any data. Or sometimes the machine take the data and then based on some internal QC or quality control algorithm, it thinks this data is not correct, so it throw it away. So it's all possible. But anyway, the final result is you don't have the data there and you only see failure there. Okay, so let's begin. So first, of course, the starting point is again, put the data into R. So, and remember that we have our data, sorry, where is it? In the drug screen.csv file. So first, let's study what's the CSV file format. Again, this is not something related to R. This is related to a file format universally exists across Windows, Mac, Linux. Yeah. So CSV, not to be confused with CVS. Yeah, I sometimes call, if I speak too fast, I will give the CVS to me. Yeah, so CSV means comma separated values. So it is a widely used file format to store tabular data. It's just like spreadsheet. So for each row in a CSV file, it means a row in the table. And within each row, to let the computer know which value belongs to a different column, you simply separate each value by a comma. So that's where the comma separated value's name is from. So how you can view a CSV file? So you can view it in Excel, or you can, nowadays you can also view it in Google Sheet. And you can even use text editor like Notepad or TextEdit to open it. So CSV, many people who have used Excel might be thinking that what about the .xlsx format? When you save a file in spreadsheet in Excel, this is the default format. CSV is really preferred among data analysts who use programming language to handle those data because XLSX is too complicated. So you guys have all used Excel, or yeah. So you can have one tabular data, and then beside it you can have some graph, and you can put in some formula, and you can even add VBA codes to it. And the problem is that then everything is in that .xlsx format. So when you need to read it in, you need to carefully separate all the parts to get only the tabular data you want, which is kind of a huge pain. So people prefer this CSV format, although because it's simpler, only the tabular format is only the tabular data is there. And CSV file perhaps it's not the only file format you will encounter. So it can also be TSV file, which means tab separated values. So it just means the values in each row is no longer separated by comma for each column. It is separated by tab. That's the only difference. And more generally, for whatever separated values, we call that sign used to separate the stuff a delimiter. So comma or tab is called a delimiter. And this kind of file format is generally known as delimited file format. So CSV, TSV are all delimited file format. If some people use one single space to separate value for each column, then it's something like space separated file format. And they are all like known as delimited file format. Okay, so why I'm torturing you about this file format is because you need to know it so as to use the function, the correct function in readr package in the tidyverse to import the correct file format, the file format into R. So it offers three functions: read CSV, read TSV, and read delimit. Because CSV and TSV is so commonly used, they have a dedicated function. For other delimited file format that use rare weird delimiters, you use the read delimit, and by specifying which delimiter they are using. So, and the key to allow, and in our course, we will just use the read CSV, and the key to use this function is to let the function know where is your file to read. So where is your CSV file to read? So then we need to learn another concept called path. So in our computer, we store our files into different, no matter which you want to call it, a directory or a folder. And then within a folder, we have another folder. So that's how typically you organize all your files in your PC or Mac. So full path is a text starting from the root directory, which means the very, 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 very mother directory holding all the folders you have. Although you perhaps have never visited that directory, but when you are using your Mac or PC, but it does exist. So the full path means from the very, very beginning one, what we typically call the root directory, all the way to your file name. And in Windows, Windows tends to separate each folder's name by the backslash, and Mac and Linux separate each folder on the path by a forward slash. Say, for example, the full path to the drug screen.csv on my Windows PC is something like this. It's on disk C, users, Exchange, OneDrive, desktop, rcode, QC bio lectures. This is the folder I create for this lecture. And within it, because it is a data, so it's in a folder called data and drug screen.csv. And because this is Windows, so I have backslash. So for any file that's on your PC, so you can use the properties menu to call out its full path. Yeah, like this. And then one thing specific for Windows user, unfortunately, is that Windows, for whatever reason, decide to use backslash to separate each folder. But unfortunately, in R, backslash followed by one character carries some special meaning. Say, for example, backslash n means change to a new line. And for this reason, you cannot use this file path you get directly from Windows. You either need to change all the backslash to forward slash, or you just double backslash to escape the slash sign like this. Then this becomes a valid full path of your file that R can understand. For Mac and Linux user, you don't need to worry. So they are naturally compatible with R because they use /. But it can be very annoying because typically we don't put everything in our root directory. Instead, we prefer to organize into different folders, and this makes the full path very, very, very long. And if you want to read in multiple files, every time you are pausing that very long name describing all the folders from the root directory all the way to the folder containing it, it's very annoying. So in R, there is a function that can save us from all this trouble if you are reading files from the same directory. That is set WD. WD means working directory. So it means once you set WD to a specific folder, then for all the files within that folder, you only need to refer to it by its file name rather than the full path, because R knows your working directory is this folder. So it no longer asks you to provide the remaining part of the file name or the remaining part of the full path. So this can be very practical because usually within one data analysis task, we're dealing with file in a specific folder because that's how you group them. So okay, so here is let's say so first I set the working directory to the QC bio lecture one. So I just set WD all the way to this QC bio lecture directory to avoid trouble. I wouldn't immediately switch to RStudio to show you guys, but I will show at the end. And then now I only need to pass the file name, but there is one thing is that actually this screen.csv is within another subfolder in the working directory. Don't worry about it. You can just type in the subfolder name / and then screen.csv. Then R knows it will add the working directory together with this part to form the complete path, the full path, and get the file name you want. And at the same time, you notice we have another 2 arguments here. So the first column names is for indicating whether your CSV files contain a column name row as the first row. So there are 2 styles of storing your data. Some people prefer to put the first row as the name of the column. Some people prefer to just omit it. Then you need to allow read CSV to know which style you are using. Is the first row just for column names, or is the first row directly for data? So if it is true, then the first row of your CSV will become the names of the column. But if it is set to be false, then the first row will be directly regarded as data, and the column name will be left as default. And then there is another very important function, especially if you know your data contains some unavailable data points. Say, for example, the failure we have mentioned before. So they are not available. So NA means not available. But practically speaking, although the most standard way of labeling not available data is NA, but for historical reason, there are lots of ways like people prefer to use to label data that's not labeled. Say, for example, failure, not measured, NA, N.A. So it's very annoying because there is no consistent pattern. And that's why read CSV, including a handy argument, allowing you to specify which value in your data would be treated as an NA value in R. So in our case, it would be failure. Because the technician has already told you for whatever data that's failed to be measured, it's labeled as failure. When you are working with manually entered data, this pattern can be sometimes very inconsistent. Say, for example, today, the data is collected by a PhD, and he labels any data that's missing as not measured. Tomorrow, an undergrad come to help with collecting the data, and he labels all the data that's not collected, failed to be collected as failure. And then in the final data, you have two values referring to the same not available, which is not measured and failure. In this case, you can simply put failure and not measured as a vector, and all these two both of these two values will be treated as NA by read CSV. So that's a very convenient argument for you to handle NA values. So then let's preview. So let's say we run this function, and then usually the good thing I recommend you to do is that once you import the data, don't immediately begin to work on it. Let's first check whether the data is imported as you expect. So there are two ways of checking it. So first, RStudio offers you a very convenient way to check it. That is, once you import your data by the read CSV, you will see the data with the correct variable name pop up in the top right corner of your of the RStudio panel. And then you can simply click this data, and immediately a very familiar spreadsheet-like overview will pop up on the left-hand side corner, on the left-hand side, as a new pop-up window. So you can see, oh, we're reading it. There is a mysterious 1, 2, 3, 4, 5, 6 row at the beginning. So there is a column corresponds to sample ID, which makes sense. That's the ID for each measurement. And we see some numerical values for the reads, all make sense. And here you can see that by going to this here, you can even see there are 603 observations, which means all the data are correctly imported there. Okay, so let's go back a little bit. Or if you want to look more like a professional, you can use a function called head to just give you a few rows near the head of your table as a brief overview to check whether the data is correct or not, rather than interactively click on RStudio to do that. So the reason why I recommend you to always preview your data by after you import it is because sometimes you import the wrong files with some small typo. Say, for example, drug screen V1 and drug screen V2. I mean, if you miss just one digit, then you import a completely different data. So it's always good for you to check whether the data is imported. And in some rare case, but I have definitely encountered, is that you do not read the file with the correct delimiter. So this is a rare case that happened to me once. So someone gives me a file whose name ends with .csv. So without second thoughts, I think this is a CSV file, and then use read CSV to read it. But then when I preview my data, I find that all the columns are collapsed into one column. And what's the cause is because although this file is named as .csv, internally it's actually type delimited, which means it's a .tsv file named as .csv. by the way, most operating systems give you the authority to change this name, so it can indeed happen. So you might in the future encounter a file that's delimited by, say, for example, tab, but named as CSV. So in this case, first you are just like me, you perhaps will just use read CSV to read it, but you will save yourself from all the further waste of time by just preview your data to see whether all the columns are correctly separated from each other. And the reason why, if you use it wrong, can cause all columns collapse into one is because the read CSV rely on dot to tell it needs to switch to a new column. But if it's actually a TSV, then it will never encounter a comma. So everything is in the same column. So this is the reason behind. So always check your function, check your data after you import it before you begin analyzing it. Now let's have an exercise, because our data is now already imported as a data frame into the R. So you are ready to apply all what you have learned from section 1 to section 3 to analyze it. So let's have an exercise. So the first thing you want to evaluate is how much percentage of the reads actually failed, because the technician only tell you some of them failed, but doesn't give you a specific percentage. I mean, if the percentage is very large, like 75%, perhaps you don't even bother to analyze it, just redo the experiment. But if it's just like 1%, then perhaps you should tolerate and move on with all these NA values. So how to calculate the percentage of all NA in your reads? So think about this. So essentially you have 603 reads. I mean, first, you shouldn't count it one by one by opening the preview and count it, right? You should use some program to count it. So you need to check whether the value is NA or not, and you want to loop through all the values to check it, right? So again, you don't need to really write out the code, but you should roughly have an idea of how to implement it. So here is my way of implementing it. So first, we have a counter of failure, which means this variable counts the number of failed reads for us. And then I loop through all the drug screen data's rows. And then within each row, I use, so recall from the first day, we can get the column from drug screen data by use the $sign and following by the column's name. And then we can use the square bracket followed by an index to get the specific row. And I cycle through each read. And whenever I find a read is not available by using the is.na function. By the way, you haven't learned this function, but you know how to figure this out by asking AI or read the technical documents. And then whenever, you see here I use if. Whenever a value is NA, I add 1 to the failure counter, which means one value is detected as NA, and I just scroll up the counter by 1. And finally, since we want to know the percentage of failure, so when we end the for loop, we should have all the number of failures in the failure counter, whether it's 4 or 5. And then because we want a percentage, we divide it by the total number of reads. If you are too lazy to remember it's 603, then you can simply use number of rows to unroll to get how many number of rows are there in your data frame, because each row is one measurement. And then finally, we print out the failure percentage. So this is how the code is work. So perhaps the only thing you don't know is the function, which is is.na and enroll, but you have already learned how to figure this function out on our first day of lectures. Now here is some more professional way of doing it within just one line. So if you remember yesterday, I told you that when we teach about data coercion, I told you that if data coercion is used smartly, you can write very cool code out of it. So this is the example I promised to you. So in the previous, we used around 10 lines to realize the counting of percentage of failure. Sorry. And here, we will just use one line of code to do everything that 10 lines of the code do. So let's see what it is doing. So first, I applied the is.na to the whole column of read from the drug screen data. I know it can handle this because I read the technical document. is.na can accept a vector of input and check whether each element of the vector is NA or not. And then what it returns to you is a true or false logical vector. Because when it is NA, then it is true. And when it is not NA, it is false. Okay, we finish this part. And then what I do is I calculate the sum of this vector by the function sum. Sum, I mean, it's very clear, it sums things up. And how do you sum things up? You give it all the things you want to sum as a vector and sum them up. Again, if you are not sure, just read about the document of sum. But then comes a question like, what is true plus false, right? They are logical numbers. They are logical values, not numerical values. Like, how do you define true plus false? You don't know. R also doesn't know. But R think it can help you because logical values, as we have shown yesterday, can be coerced to numerical values. So true is coerced to 1, and false is coerced to 0. This coercion rule is some history deeply rooted in the field of computer science because computers only handle binarized value, which is either 0 or 1. In the very old computer, a light lights up means it's 1. A light that's dim, a light that's dark means 0 or false. So that comes why true is like coerced to 1 and false is coerced to 0. In any other programming language, I think this is the rule. So true to 1, false to 0. And after this data coercion, then because all the false becomes 0 and all the true becomes 1, so when we sum up this coerced vector, the value we get is simply the number of true in a vector because the false doesn't count. Like false is 0, so you sum lots of 0 up, it's still 0. Only those who will contribute to the final value, only the true. And because true is 1, so how many trues you get, that's essentially the final result after the sum. And then we divide by the sum, which means how many trues are there in this vector, which means how many NA there is, and divide it by the number of rows, which is those samples. And this is exactly the failure percentage you get. So you can do this without for loop. It's just one line. And actually, it's much easier to read, right? You first check whether it's NA, you sum everything up, you then divide. So it's not only like concise, it's also much easier to understand than a 10-line for loop. So this leads to the concept of vectorization. So vectorization means replacing the for loops of or while loops to visiting each element in the vector by some functions or whatever manners capable of handling all those elements all at once. So vectorization generally have two major advantages. First, if you use it promptly, it makes your code cleaner, which means more concise, 10 lines to one line, sometimes 100 lines to one line, and more readable. And in some cases, it can significantly speed up the processing of large vectors. The reason behind it is that if you can find a function who can handle a vector as an input, chances are that this function might be optimized to handle those vectors in a very, very fast manner than just using a for loop to go through them one by one by one. So it's just some very smart guys come up with some ways of processing a large vector like simultaneously in different elements, and then in a much faster manner. So nowadays in our computer, many of the computers have multiple cores in it, which means each core can work separately. So some bottom level functions are optimized such that if you give it a vector, it distributes each element in the vector to different cores. So the speed is like, if you have 10 cores, then the speed is 10 times faster. Rather than you use your like for loop to visit them one by one, they are doing it 10 elements a time. So you can also become much faster. But this is not always true because there are not every function is optimized to take advantage of such kind of designing principle of the modern computer. But yeah, I mean, as an added advantage, it's not bad. So what I recommend you to do at this point, as you have just begun to use R, is that after writing a loop, especially those relatively simple ones, it is a good practice to think about whether you can use a vectorization to replace this for loop. Because for those simple ones, it's highly likely you can replace it with vectorization. However, just be aware that vectorization does not work for all functions. So you cannot assume any function that can take one number as an input can always take a vector of more than one number as the input. So read the documents before you really try. And finally, so before teaching this class, when I was a PhD, I teach MATLAB. And at the end of the lecture teaching vectorization in MATLAB, vectorization is also a very important concept in MATLAB. I speak out the sentence I regret for my whole life is that vectorization makes you look like a professional MATLAB user. And then the second week, all the homework I receive contains all sorts of very weird forced vectorization that I don't even imagine it's possible to do. And one student even asked me, oh, there is one for loop there I really cannot vectorize. Can you give me some points? Because I don't look very professional. And I was like, okay, I actually expect you guys to use for loops for most of the homework. And it takes me like triple the amount of the time just to dive into those very imaginative vectorization to see how they are designed to be vectorized and whether it's correct or not. So whenever you feel that your element-wise operation is kind of complex, as we will soon see an example, really just use for loop or use while loop. Do not force vectorization if you feel it's a little bit complex. Yeah, I mean for checking whether each element is an NA or not, for tasks like this, it's very simple. So you should think about vectorization. But if you want to do lots of stuff to each element, and perhaps each element needs some if judgment, then chances are that it's not a good scenario to use vectorization. Luckily, there is not too much homework for this. So yeah, for this class. So yeah, don't show me very imaginative vectorization or to show off your talents in R. So And given that we have touched the concept of vectorization, so, and at the same time, I should remind you that this section is teaching you how to use tidyverse. So the Perl package in tidyverse offers you some tools to vectorize those functions that are not designed to be able to vectorize, which means even if the function only take one single element, can only take one single element as an input, by using the functions such as map, those map functions in the Perl package, you can vectorize them. So essentially the map function just take what function you want to apply, and then internally it's like loops through it to apply it for you. So it just free you from writing your own for loop. Instead, it gives you the function to help you just apply the function to each element you want. So at this stage, I do not recommend you to use Perl for the following reason. First, Perl still cannot replace all the loops in R. So loops are still very, very important flow control ways in R, and you will use them a lot in the future. So you still need lots of practice as a novice. And using Perl reduce the practice you can get. And the second thing is that vectorization is, although the code looks simpler, but the internal logic, like what needs to go on in your brain is actually more complex. So it's more prone to mistakes or bugs. And you need more experience in R so as to judge whether a bug has occurred or not. By the way, bug doesn't mean, like, if you don't get error message, it doesn't mean you don't have bugs. Code can run perfectly with bugs. It's just the logic is wrong rather than the code itself is wrong. So all in all, to conclude, you learn how to work first before you begin to run. So the purpose of this slide is just to bring to your attention that there is a package in tidyverse called Perl, allows you to vectorize your code when you feel you are expert, you have enough expertise to handle it. So we wouldn't touch too many on Perl. I think this is the end to the introduction to Perl for this class, because we are all at novice level. Then let's go back to our data analysis. So if we go back a little bit, so we see a quite meaningless column here, which is the first row with the column name .1. And it's just 1, 2, 3, 4. It's just the row number. So this row is kind of very redundant, meaningless, doesn't very helpful, not very important. So like, at least for me, I don't like dirty stuff. So sorry. Like, how can we remove a column? Say, for example, in Excel, you click that column and then you hit delete, it delete. Sometimes if you do not select the whole column, then Excel just instead delete one element. And then you're like, then you select the column and hopefully this time Excel get it right. So in R, or specifically in tidyverse, we can use the select function from the dplyr package to delete a column. So what you do is that first you can keep the columns by because it is select, there are two ways you can delete a column. First, you select the columns you want. Say, for example, we want to throw away column 1, and so it is equivalent to just keep column 2 and 3. And or you can refer to it by the name of the column you want to keep. Or in another way, you can delete the columns by exactly specify which column you want to delete, followed by a minus sign, which means minus this column from my data set. So you can easily imagine, so if you have lots of columns to delete, then perhaps it's easier to select the ones you want to keep. If you have lots of columns to keep, then it perhaps is easier for you to specify which columns to throw away by putting a minus sign. And one thing you might notice here, a little bit counterintuitive, is that I'm referring to a column's name, but I put it as if it's a variable without using the double quotes. So long story short, in tidyverse, you can either put double quotes or omit the double quotes. Omit double quotes is recommended because you are handling data. Tidyverse assume you are handling data frame a lot, and thus you need to refer to a lot of column names, and it will be very tedious if every time you need to add quotes to it. So just to give you an idea, so this function select can become even more powerful if you want it to be by combining it with a group of function called selector help, called a selection helper function. Say, for example, you can combine select with the start with function to pick out all the columns whose column names start with certain text. Say, for example, if you have sample 1, sample 2, sample 3, instead of typing sample 1, sample 2, sample 3 column names, you can just use this one line of starts with sample to pick all the columns whose column names start with sample. Okay, then we can move on. Now we delete the first meaningless column from our data. Let's see how can we add something to it. So remember that for every reads, usually you have some background values you need to subtract from it so as to reflect the true value, right? And it is usually good to keep the raw data as a separate column rather than directly overwrite the raw data. So what now we want to do is that we want to add a column whose name is read minus bg background to store all the values after minus the background. So we can do this with the function called mutate. So that this function is indeed, the name is not quite intuitive. So the idea is that whenever you add something to your column, you kind of mutate it. To the data frame, you mutate it. So what we do is that we mutate, and then the first thing is what's the data frame you want it to handle, and then you add the new column name here, read equals to read minus 0.5. So sorry, here you just use the old column name. So in this way, all the background minus the subtracted values will overwrite the original values in the read column. This is not recommended way. So instead, we can put the new name of the column here, and then say use this to refer to the column with the raw read and subtract 0.5 from it. So what R does is that it finds that this column doesn't exist in your current data frame. So it creates it and store all the values from read minus 0.5 to it. So that means make sure you type the name of the column in the exact way you want. So say, for example, if you want to refer to read, but you accidentally type as, say, for example, read, then R will think, oh, this column doesn't exist. So let me create a new column whose name is read for you. So be careful, your name must exactly match whatever you want to do to the column. Okay, so we still have some time, so that's good. Now let's take a look at exercise 5.2. So currently, if we just look at our data frame, so we only have the read value and the sample ID. Sorry, it doesn't look like this. So it only have the reads and sample ID. It's a little bit hard to tell that which measurement is for which drug and which measurement is for which replicate. So let's add two new columns. One is called drug, the other is called replicate to it to indicate what's each read and what's the drug for each read and what's the replicate for each read. So, one trivia thing. So why do I name it as drug 001, 002 rather than drug 1, drug 2? Is because it is easier to sort names like 001, 002 rather than 1, 2, 3, 4, or 1, 2, 3. So here I just give you an example. So if you sort something like drug 1, drug 2, drug 3, drug 10 will goes in front of drug 2 and 3. That's simply because R looks through compare 1 digit by 1 liter by 1 liter and find that 1 from the 10 is smaller than 2 and 3. So that's why drug 10 comes in front of drug 2 and 3, even though this is not how we human prefer to sort it. So what's the way of fixing this problem is you add zeros in front of the numbers such that the 10 is now in the second, the 1 is now in the second letter here and versus all the zeros. Now R knows 1, 2, 3, and 10. So all in all, this is just a way of naming your elements to make it easier for R to sort them and save you from like weird mistakes. So then how like you definitely don't want to type in drug 001 and something like that for 603 times. So what we can do is we use a built-in function. So please note this one is not from tidyverse. So this is just a built-in function, allowing you to generate some text based on patterns. So here is the how it looks like. So you first specify the pattern by saying it's drug percentage sign D, and the percentage sign D is recognized as a keyword by sprintf, meaning that you want to put a digits here. And where is the digit coming from? You pass it a vector saying that it's from 1 to 200. Then it will give you something. So sprintf will return you a vector of character from drug 1 all the way to drug 200. How do we fill? Like, how do we fill the digits with extra zeros? You just, after the percentage sign, you add another keyword called 03, which means pad 0 up to 3 digits for me. And then it will become drug 001, 002, and 200. So homework. So is percentage D the only keyword you can use in sprintf? Are there any other keywords? So you should already know the way how to figure out this. So that's why it's a homework. And then there is still one thing we are missing. So if we go back to this column, simply have drug 1, drug 001, drug 002 is not enough. We want it to repeat itself 3 times before moving on to the next drug due to the unique like organization of this read column. So still remember the repeat function we used before. So we can use it to generate 2 types of repetition. The first one is like you repeat like ABC, ABC, ABC. If you want it like this, you specify the times argument to it. And if you want it to repeat in another manner, which is AAA, BBB, CCC, which means drug 001, drug 001, drug 001, then drug 002, drug 002, drug 002. Then you use the each argument rather than times argument. So with one function, by specifying two different arguments, you can generate two different patterns of repetitive characters. And this exactly meet our needs. So what happens is that we can use replicate time, rep times to produce this column, and we can use sprintf and coupled with rep each to generate this column, and then we can add those two columns to our new data set by mutate. But then there is a problem is that currently the order of the column is incorrect, because when mutate adds column to your data frame, it always adds column to the left side, to the right side. But intuitively, we want it to look more like this. The drug is the first column, replicate is the second column, and read is the third column. So what can we do is that we can again use the select function to reorder your columns. And the key idea is that you just reorder it based on, you just reorder it by reselect it. So here, what you select the column in the order of sample ID, drug, replicate, read, and read minus BG. This automatically gives you the data frame with the desired column orders. And if you still remember the helper functions for select, right? So if you have many function names and you only want to put two columns to the beginning, then you only need to specify the column name of the columns you want to put to the beginning, want to stay at the beginning. And for all the remaining columns, you just use the everything function, meaning that please keep everything the same for the remaining columns, such that you don't need to type in the column names one by one. So then, because now we make our data like very clear, so it essentially looks something like this. Sorry, you also have a read minus BG column after the read here. I just forgot to show it here. So now it looks very clean, which is good. So we can begin to analyze it. And given that we have multiple replicates, the first thing we want to do is we really need to calculate the mean of each replicate and the standard deviation of each replicate. So again, we need to loop through all the reads and then calculate something. So I think solution one should be your first intuition. We want to apply something to all the reads in some to lots of reads. Then we use a loop to loop through it. But the only thing I need to remind you is that this one is a little bit complicated, because in our original data, every 3 row belongs to a specific condition, meaning that they are just replicate 1, 2, and 3, which means we need to group them together when we calculate the mean and the standard deviation. So this means you need to, when you for loop, you cannot just brainlessly visit each element. Instead, you should visit one element and associate the other 2 with it and calculate the mean. And this becomes the mean to be used by these 3 replicates. So that's why you see here, instead of loop all the way to the end 603, I just loop 1/3 of it, because there is only 201 mean and standard deviation to calculate with this for loop. And then within this drugs within each loop, so I refer to 3 elements based on this I condition, which is the other 2 replicates associated with that one, and calculate the mean and standard deviation of to calculate and store them for mean in each condition and standard deviation in each condition. So overall speaking, the only complexity added to this for loop is that you need to be aware you are grouping every 3 elements together for calculating the mean and standard deviation. And perhaps a good exercise is to look at this and figure out how understand how it exactly works. But I think you already appreciate the complexity it is added to the for loop. It's no longer as simple as it used to be. So tidyverse offer us a way to avoid this complex for loop. So instead, we say that, oh, we want to group like replicate together. But we already have a column telling us how to group them, which is, let me just remind you, sorry. Which is this drug column. So all we need to do is that for all the reads that belong to the same drug or control, we group them together to calculate the mean and standard deviation. And that's all. So how can we do that? So the tidyverse developer has already think about this for us. So what they give us is a function called group by. So first you say that let group by my drug screen data with the column with the values in the column drug. So you can, like, after you run this line code, nothing happens. Like everything looks like peaceful, like nothing happens. But then the miracle happens when you use mutate to add mean and standard deviation by simply use mean and SD plus the values in read minus BG and read minus for SD for standard deviation and mean. So yeah, I think so what you will immediately see is that here we immediately have 2 new columns, and magically for each 3 of them which belongs to the same group, they get the same mean, which is exactly the average of these 3 values, which means when adding a new column based on mean and standard deviation function, R, for whatever reason, knows that it should group like each 3 row together, which have the same value of drug and control or whatsoever. So what is really happening after this group by? So if you inspect the data frame, so the mean and standard deviation column are added by the mutate. And you don't see any new column added by the group by function, which means it doesn't add anything to your data frame. But how does then the mutate function know now it needs to group every 3 rows together? So the magic is that it adds something called an attributes. It added something that's known as an attribute to your data frame. So the attribute is stored separately from the raw data of your data frame. So for all those numerical data, like the spreadsheet, like numerical data, they are stored like here. And then group by just add something called group and point the group to the drug column elsewhere. And they both belong to the whole data frame, which means when you check your data, you only look at here. And that's why you wouldn't see the group attributes that's hidden there. But when the mutate function comes, it purposefully checks whether there is a group attribute assigned by the group by function. And if it finds there is one, then when it adds like new columns based on these functions, it purposefully group each row based on what's specified in the column in the group attribute to give you the new column. So this means, and the grouping attribute, it is a trick used by the dplyr package. And mutate is also from the same package. That's why it knows to check whether there is this attribute hidden in your data frame added by group by. If you are using other functions from other packages, it is likely that they are not aware of this trick unless they are specifically designed to work with dplyr. Which means if you want to use group by, you'd better also use other functions in the dplyr package to make sure they are aware of this group function. You may also be wondering, like, how can I check this hidden, like grouping attributes silently attached to my data frame by this group by function? So you can use another function called groups to visualize it. So you use groups followed by the name of your data frame, and it will pop up. Is there any column for grouping your data assigned by group by? If you want to work very cleanly, saying that I only want the group to apply for this specific part of the code, you can add ungroup, put your name of the data frame variable here to kill all the associated grouping attributes associated by the group by. Now you ungroup it to make sure nothing carry over for your subsequent codes.
I have a question. So when we are using this mutate function and group by, let's say if I have multiple like drug and there's another grouping, do I need to tell that which one is going to be used for the grouping? Let's say if there's another one called male or female, or which type of drugs, if there's another column, how will that be taken into account? Where are we specifying that we need to take that particular group?
That's why in group by you have the second argument specify which column to use.
So if
Drug. Yeah.
So if you say, you have to say the column name.
Yeah, you have to say the column name
Okay.
of which one you want it to group by based on. Yeah. You can also clean the drug assignment by ungroup and then assign another group for a different purpose later on.
Yeah. Okay, thank you.
And finally, so currently our data frame, the spreadsheet, the data frame looks like this. It's a little bit non-intuitive to read because you see like say for example, like one condition have 3 rows, and which makes it very, very long. And for mean and standard deviation, it replicates itself every 3 rows for reason we know. But for people who first read this spreadsheet like data, they will be very confused, like why the mean looks same for every 3 rows. So what we can do is we can transform or reshape our data frame into a more user-friendly manner like this. Now, each row just belongs to one drug or one control. And the reason why we are able to do this is because we stretch the read column into replicate 1, 2, 3, and of course, read minus background 1, 2, 3. So we are transforming our data frame from a very long one, which is difficult to scroll through, into something that's wide and more intuitive for human being to understand, where each row is just one condition. So how can you do that? So the magic of doing that, you have another function from the tidyr package. It's no longer dplyr, but anyway, it's in the tidyverse. We can use the pivotal wider function to convert our data frame from long format to a wide format. So here is how you're going to use it. So let's start from the bottom argument, which is the values from. So values from is simply telling the pivotal wider function, okay, which columns do I need to drag into the wider format? So it's, in our case, it's the read column and the read minus background column. So for these ones, we want those separate values to get dragged into separate column to make it wider. And then because when you make it wider, you create new columns. So in most cases, you want to name those new columns, and they the pivotal wider like give you some very easy to use argument for you to create those names. The names from argument says which column from the original long data frame should I get part of the functions, the column's name. Here we say it's replicate because it makes sense. So here we have replicate 1, 2, 3. And when we stretch the column longer, we also want it something to be replicate, the column name to be something like replicate 1, replicate 2, replicate 3. But the problem is that it's not enough. So because the values in the name from in the replicate column is only 1, 2, 3, something like that. So sometimes it's not enough to only add 1, 2, 3 to that, because you see here I also add like read minus bg replicate 1, replicate 2, replicate 3. So what you can do here is you specify names prefix, meaning that it will attach this prefix replicate underscore to all the values in replicate. And when it's done, it put all these, the complete replicate 1, replicate 2, replicate 3 to the end of the current column names to be stretched, which is read minus bg or read. So this is why the new column names look like this. So the first part comes from the original column name, which is read or read minus bg. And the second part comes from the name's prefix, which is replicate. And the third part, 1, 2, 3, comes from the value of replicate, the value in the replicate column. And at the same time, we remove the sample ID column, as you can see in this first argument. Instead of passing just the long data frame into it, we pass the long data frame, but we minus the sample ID by select. The reason is because this column cannot be collapsed into a wide format. Because you see why drug column is fine is because for each 3 row, the name is the same. So you can collapse it by simply omitting those redundant names. But for the sample ID column, each column's name is unique. So the pivot wider function wouldn't know how to handle this because it cannot be easily collapsed into something like the drug column in this case. So that's why we need to subtract those columns that are not compatible with being converted into the wide format at the beginning of the pivot wide function. Yeah, so that's how you convert a function, a long data frame to a wider data frame. You think about 3 things. First, what are the values what are the columns I want to stretch into the longer format. Then you think about, oh, for those new columns, based on which columns do I want to name them from? And by the way, the columns that's like used to name them also automatically disappear because it turns into the name of those new columns. And finally, you think, what are the columns remaining that cannot be easily converted into the wide format? And then you drop them. So by doing all this stuff, we end up with two types of data frame. One is long, the other is wide. The wide one is easier to read. And in tomorrow's class, we will see what's the use or what's the advantage of also having that long one. So all in all, so this ends our class today, quite precise on time. So here is a temporary conclusion on section 5. So we will keep talking about tidyverse tomorrow. We will use, but today what we have learned is how to use functions from read_r to import external data. I introduced to you the concept of vectorization and tell you that Perl is not recommended at this moment, but when you become more professional, you are welcome to use it to vectorize to replace for loop. And then we learn multiple functions of how to handle all those columns in your data frame by the dplyr packages. And finally, we learn how to convert the shape of your data frame by using the tidyr packages pivotal wider function. So tomorrow we'll keep introducing other functions in tidyverse library to keep on working on our drug screen data. Yeah. I will say, because we are already about to reach 4:30, so I wouldn't do the demonstration or in the RStudio, but don't worry, we don't have too much content tomorrow, so I will just move the demonstration in RStudio to tomorrow's beginning of the class. Yeah. That's all. So thanks for following.